Okay, today we're going to continue with the electromechanical coupling coefficient. And we learned last time by applying an electric field, we calculated the electromechanical coupling coefficient to be d squared over SE times EX, capital X. And using the mechanical applied field, we found the k squared term to be equal to d squared times E little x. Remember, this is constant strain, this is constant stress, this is constant electric field. So we had SD, and we had E capital X squared. So these are the two relationships, and actually, as I claim, they are equal to each other. So let's take another look at what happens when we apply an electric field from a energy perspective. And I mentioned, let's draw the figure. Let's say we apply an electric field, we try a positive here, and we apply a negative here, so we get an electric field going that way, so the material, again, it expands. So let's take a look at the energies here. So one way we can kind of look at this is we can look at from the perspective of the power source. From the perspective of the power source, this material has a permittivity which is equal to the permittivity under free stress. So there's no stress going on, and we have a permittivity indicative of the capacitive energy stored in the material. So we know from our previous equations that this is none other than equal to the epsilon of this number. Let's go to the next slide. So we had this is the input energy. So let's define k squared again. So we had the input energy UI, U stored, and U converted. So let's just write it out. UI equals U stored plus U converted. In this case, when we are applying an electric field, the input energy is equal to the capacitive energy, which we defined earlier using the dielectric permittivity under free stress. Then we can have the area times the length. The length is also the thickness in this case. The length times the area. And then the stored energy, the stored electrical energy, is similar. Oh, sorry, we had the E squared here. Okay, electric field squared. Then 1/2 times the epsilon under free strain. So the stored energy, electrical energy, is the stored energy under free strain. Because basically what gets divided out here, which I'll be explaining in a second, is that the input energy, which seems like a capacitor from the perspective of the power source, actually inside the material it's being converted into pure electrical energy and mechanical energy. And mechanical energy under what condition? It's being converted from the mechanical energy under elastic compliance. So AL over SE times the strain squared. So this is the relationship between the input energy UI, US, and UC. This is the energy flow in a piezoelectric material where we apply the field. And now by solving this equation, we can derive the relative relationships between these parameters. See, what we're actually trying to do is derive how is this permittivity under free stress, how is that related to the permittivity under free strain? And we know it probably has something to do with the coupling coefficient, but what kind of relationship does it have? This is the problem which I'm trying to solve here. So immediately we try to reduce these equations. So we have the epsilon x. Well, let's divide through by 1/2 area L. So what we're left with is this. So now we're left with this equation. And again, why don't we use SD over here? Because SD both includes electrical and mechanical energy. And I'll be giving another description of this quite soon. So here we go. Let's continue. So we have this permittivity, and then now again, this is under constant electric field. This is a superscript. So now we don't have these equations balancing out. I mean, these obviously when we divide through by electric field, we're still going to have electric field left. So we have to relate electric field and strain, and none other than those simple equations we derived earlier. This is the relationship between electric field and strain. So let's substitute. In there. So we have this. We can divide through by the electric field. So okay. This is looking very interesting. So look. What now we come up with a very cool, very interesting equation, that the permittivity under constant stress, as I mentioned, this was like the input energy, which had more energy technically because it has both mechanical and electrical energy stored in this one term, is equal to the permittivity under free strain, which is plus the d constant squared divided by the elastic compliance under constant electric field. So this actually, we can tell that these are related by this term. And now we can also use this equation further, and we can further understand this equation by the following explanation. So let's say we divide through everything by E under constant stress here. So we're simply dividing through. And what does this equal? Just running out of space a little bit, but this equals 1 k squared. Because remember, what was this? D squared over SE e to the capital X. See, when we divided through by this number, we divided through by this capital X here. We actually put a capital X here. Sorry, I didn't write that. We also put an e to the capital X there. And then this number is none other than k squared. So by doing this, we have the following relationship. We got that, which is also equal to a simpler, a more common definition. Sorry. All right. So how's the weather out there? Okay, anyway, so this is what we have. This is the main relationship, and I'll rewrite this on the next slide. So the relationship that we are looking for all along, the relationship between the permittivity under free strain, under permittivity under free stress, in constant stress equals 1 minus k squared. This is how these terms are related. Now obviously, this term is bigger than this term. This is always 1 or equal to, 0. It's between 1 and 0. So therefore, this term right here is always between 0 and 1. Therefore, this term is always bigger than the permittivity under free strain. I mean under constant strain. And in the next video, I will derive the relationship between SD and SE. Thanks for watching.